Welcome back. In this video, I'm going to talk about the geodesics in Schwarzschild metric. I shall be trying to calculate the geodesic equation from the expression of this given metric. But I want this video also to be a tutorial on how to find out geodesics from metric in a much shorter way. So let me first describe to you what is the usual way of determining the geodesic equation from the metric components, and then we shall use an alternate method which requires much less time in order to figure out the geodesic equation directly from the metric itself. So let us first look at the formal way of finding out the geodesic equation. Well, here we have a general form of a given metric. Here G mu nu, written in red, are the metric components, and x mu and x nu are just referring to the coordinate system we are using. So obviously this components in general depends on the coordinate themselves, so they are also functions of coordinates, and they are the one that carries the bulk of the information that are required to find out the geodesic equation. Now if you remember the geodesic equation, they're written like this. So it's the double derivative of a coordinate x mu with respect to a parameter. Now for the simplicity of this content, we are going to assume that this parameter is an affine parameter. Otherwise, the structure of the geodesic equation changes. So then this is the first part, which is akin to acceleration. And then we have gamma, mu, nu, rho. And these are called the connection coefficients. Connection coefficients. One little but important information about these connection coefficients are that these are not components of any tensors, right? Because they do not follow the tensor transformation rule. And these coefficients are symmetric in these lower indices. That means nu and rho. We aren't done yet. This is accompanied by x nu differentiated with respect to d sigma and x rho differentiated with respect to d sigma, and this is equal to 0. So had sigma not been an affine parameter, we'll have a non-zero contribution on the right, and this is the advantage of using an affine parameter. So for example, in case of massive particles, the proper time is an affine parameter, and any other parameter would satisfy this equation provided that that parameter sigma is affinely related to the proper time. That means a constant times the proper time plus another constant. If sigma is related to tau, which is a proper time, with this equation here, then sigma is called an affine parameter, and sigma is said to be affinely related to tau. But I guess at this stage you're supposed to know this, right? Now the most important part of this equation is to find out the connection coefficients, and that is the task that carries the bulk of the work in terms of computation. How do we find out the connection coefficients? So there is a formula, and the formula says the connection coefficient gamma rho mu nu can be written as half times g rho sigma, where g rho sigma are the components of the inverse metric, right? And then we have the derivatives of the metric itself. So we have g mu sigma comma rho, where this comma indicates partial derivative, and then we have g sigma nu comma mu, so it means it it is the partial derivative of this metric component with respect to x mu coordinate. And finally we have g mu nu comma sigma, and that is our desired expression. So basically you fix rho here, which have 4 possibilities, and then you have to consider all the other possibilities that you can plug in here. Obviously the symmetry in the lower 2 indices gives you an edge in terms of calculation, but that's pretty much it. So it's a long calculation, as you can imagine. But we're not going to take this path. We're rather going to use something that is already known to us, and that method reduces the amount of calculation drastically and gives us the exact amount of information we would have derived had we followed this method. So let me show it to you. Alright, so this is what we are going to do, right? So we have a metric which is like this: ds squared equals g mu nu dx mu dx nu. Correspond to this line element, we can define a Lagrangian which is like this: g mu nu, and then we have x mu dot, and then x nu dot. Alright, so this dots simply means they are derivatives with respect to the parameter, the affine parameter we have just chosen. So if that is the case, then we can write down the Euler-Lagrange equation where we plug in this L as follows. So on one side we have the partial derivative of L with respect to x mu, and on the other side we have the total derivative with respect to the parameter acting on the partial derivative of L with respect to x mu dot. And this is it. This is going to spit out our desired geodesic equations, and then we can just read off all the non-zero connection coefficients we'd like to find. And this is the totality of the method, right? So when we go into action, this is what we're going to execute. So as we have just explained, this is the Schwarzschild metric, and there should be a corresponding Lagrangian, and the Lagrangian should look like this: negative c squared times 1 minus 2 mu divided by r, and then we have t dot squared. So remember, t dot means dt d sigma, and similarly for all the other variables for coordinates. And then we have 1 minus 2 mu divided by r inverse r dot squared, and then we have r squared theta dot squared, and then we have r squared sine squared theta phi dot squared. So this is our corresponding Lagrangian, and all there is left is to plug this into the Euler-Lagrange equation. So first let us choose the coordinate t, and notice what we have here is the fact that none of the metric coefficients are actually an explicit function of t. So on the left hand side we have derivative of this Lagrangian with respect to t. On the other side we have dd sigma acting on the partial derivative of the Lagrangian with respect to t dot. Now on the left hand side, the expression that we have, since none of the metric coefficients or the metric components rather, are an explicit function of t, this part is 0. And on the other side we have dd sigma, and then inside, of course, we do have a term containing t dot, which is precisely the first term. And if we do differentiate it with respect to t dot, what do we get? So the previous portion remains unchanged because there is no t dot here, so this remains exactly as it is. And then we have a 2, and then we have a t dot. Now, of course, on the left hand side we have a 0, on the right hand side we have a derivative, and therefore the quantity inside must be a constant with respect to this sigma. And if we get rid of the other constants, which are non-zero, then we end up with this expression here, which is 1 minus 2 mu divided by r times t dot equals k. And this is our first geodesic equation. Next, we choose the variable theta, and for theta, the Euler-Lagrange equation looks like the partial derivative of L with respect to theta, and then the total derivative with respect to sigma acting on the partial derivative with respect to theta dot. Do we have a metric component that depends on theta itself? Yes, we do, and it is the last term. So if you differentiate that portion with respect to theta, what do you end up with? You get r squared and then 2 sine theta, and then we have cosine of theta because you differentiated it, and then phi dot squared. What about theta dot? That, of course, resides in the third term. So what do we have? We have derivative with respect to the operator acting on r squared, and then theta dot squared is differentiated with respect to theta dot, and this is simply 2 theta dot, and that is it. So we can get rid of the 2's, so let us get rid of those at the beginning. So the left hand side doesn't face any more change, it's just r squared sine theta cosine theta and then phi dot squared. On the right hand side, both r and theta dot, both of them depend on sigma. So first we differentiate r squared. So what do we get? We get 2, and then we have r, and then we have r dot theta dot, plus then we leave r alone, and theta dot when differentiated becomes theta double dot. So divide everyone by r squared, and finally we get theta double dot plus 2 divided by r dot theta dot minus sine theta cosine theta times phi dot squared equals 0. And that is our second geodesic equation. Evidently, we are choosing all the easiest geodesic equations first, and as you can understand, the one corresponding to r should be the hardest one to find because all of the metric components are functions of r, and that's why we have left it for the last. So we have one more left before we find out the one corresponding to r, and that is the equation for phi. So as before, the Euler-Lagrange equation with respect to phi is given by this equation here, where we have the partial derivative of the Lagrangian with respect to phi, and then total derivative with respect to the parameter on the right hand side, which is acting on, again, the partial derivative of the Lagrangian with respect to phi dot. So none of these coefficients depend explicitly on phi. That's why the left hand side is 0. So therefore we have on the other side d sigma acting on the derivative of the Lagrangian with respect to phi dot, and it will act only on the last term here. So we have r squared sine squared theta, and then we have 2 times phi dot. And clearly the quantity inside the parentheses should actually be a constant. So finally we end up with r squared sine squared theta times phi dot equal to a constant which you call h. So this is the third geodesic equation, and finally we are going to pursue the one which is the hardest to find.